Okay, so thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Zhicheng Zhang. He's a third-year PhD student at the Center for Quantum Software and Information in Sydney, and he works under various quantum computing topics under the supervision of Professor Mingsheng Ying. And his research interests include quantum algorithms, quantum programs, and parallelism, and concurrency in quantum computing. Today, he will be talking about the verification of recursively defined quantum circuits. So, Zhicheng, the floor is yours.
Great. Thanks for this introduction, and thank you for inviting me to speak today. I would like to talk about the verification of recursively defined quantum circuits. And this work was recently done in collaboration with Mingsheng Ying. Okay, just a comment. So if you have any question or comments, please feel free to pause me at any time. Okay, so let's start. First, I would like to talk about the notion of recursion in classical programming. So the concept of recursion is very ancient in math and computer science, but in classical programming, often we refer to the recursive procedure calls. So when you write a program, for example, when you write a C program, you will describe this program as many procedures. And recursive procedure calls allows you to call any procedure within any procedures. And this feature will allow the programmer to write a very short program text, which generates a long computation. Here, the program text is static, but the computation it generated is dynamic. And this allows a very complicated computation to be encapsulated by a quite elegant and compact program. So we have numerous examples in the classical context. The first example will be Hall's quicksort algorithm, which is efficient and widely used in practice. We also have many recursive data structures like the linked list, segment tree, heap, and these data structures are very useful in practice, and they are all performed by the recursive programs. We also have classical algorithms that are recursive. For example, we have depth-first search, which is an algorithm on graph, and the well-known divide and conquer strategy in the classical algorithm and computing. Okay, now let us move on to quantum programming. So the recursion has been studied in the quantum context for the similar reasons. And we have two types of recursion in quantum programming. So the first type is known as the recursive quantum programming. Here, the adjective recursive comes first, indicating this recursion is essentially classical. So this type of recursion involves classical control flows and procedure calls. We also have a more general concept of recursion in quantum programming, known as the quantum recursive programming. So here, the adjective quantum comes first, indicating this is essentially a quantum recursion. So to support such recursion, we need to use quantum control flows and procedure calls. So later, we will explain what is the quantum control flows and what are procedure calls. Here, we only need to know the quantum control flows are guarded by the quantum if statements. So these quantum if statements are quantum version of the classical ifs and else statement. So if you have ever written classical programs, you will be familiar with classical ifs and else statement. And here we are just using the quantum version of it. And the quantum if statement allows the program execution to be in quantum superposition. So this should be compared with the typical quantum computing and quantum programming, where we allow the quantum data to be in superposition. Now we extend this notion to allow the program execution to also be in quantum superposition. And we will see this via some examples later. Now, here is a motivating example, the quantum Fourier transform. So the quantum Fourier transform on n qubits is defined by this unitary. This is a unitary mapping. So QFT n is the quantum Fourier transform on n qubits. It just maps kit J to a quantum Fourier state. Okay, we will not get into the detail of the quantum Fourier transform, but I think most of you might be familiar with textbook quantum circuit for implementing this quantum Fourier transform. So this is just a circuit translating the circuit for quantum Fourier transform in the textbook Nielsen and Chang. And as you can see, this description, or if you think of it as a program, the size of the program will depend on the number of qubits n. So if you have a lot of qubits, and when the n goes very large, the size of the program will also become very large. So this is not very desirable. And if we use the quantum recursive programming, actually the previous QFT circuit can be written in this program, which consists of 3 procedures. And each of the procedures are defined recursively. So here, QFT is a procedure, and this is a procedure body for this procedure, and it will cause other procedure root and QFT itself. And here is a shift for the third procedure. So these 3 procedures are recursively defined. And where is the quantum recursion? Let's take a look at this statement. So this is the quantum if statement. And we will explain what it means later. So here, quantum if statement will create 2 quantum branches. And these 2 quantum branches will be in quantum superposition. And each of them will call the procedure root itself, but with different classical parameters. So here we have quantum control flows and recursive procedure calls, because the root is defined by itself. So here we have the quantum recursion. And as you can see, this program is more economic than the textbook quantum circuit because the program size is independent of n. No matter how n large is, the program remains the same. Now, very immediate question is, given such program, how do we know it correctly performs the quantum Fourier transform? That is, how to specify and verify the correctness of the program. So in the remaining of this talk, I will answer this question. At this point, is there any question or comment?
Okay, I think I just wanted to ask, like, so when you show this like program, so if I look at this, should I how should I look at it to sort of immediately see that it's possibly doing the correct thing? I mean, given the intuition that I have of the circuit.
Oh, okay.
But maybe,
so
maybe it's not
actually
so obvious.
Actually, this program is slightly different from this circuit, so it is not translating from this circuit. It is actually inspired by the classical Coulomb and Turkey fast Fourier transform. So maybe we cannot get intuition from the circuit.
Okay.
Yeah. Yeah, but if you are familiar with the classical FFT, then you might get some intuition of how this program is written. Yeah.
I think I can vaguely record it in my head. Yeah, but yeah. Okay. Anyway, I guess when you go through some of the details, maybe it becomes more and more clear that this is the correct program.
Yeah, okay. Actually, we will have simpler examples later, and yeah, that is easier to explain. Okay.
Sure, sure. I
So
mean, I guess like here for the motivation is because you picked QFT precisely because like it has this like quite bad scaling if you were looking at the circuit.
yeah, yeah,
But with the recursive program, then like this is how it looks like regardless of how many qubits you have.
yeah, yeah, yeah.
Okay.
That's why we need the recursion, because you can write an elegant program to that has program size independent of the input. Okay. Thanks for this question. So let me continue. So in the second part, I will talk about a language for describing quantum recursive program. And to develop such a language, actually, I will talk about a series of languages from the simple to the complicated one, and step by step, each based on the previous one. And finally, we will obtain a language for describing quantum recursive program or recursively defined quantum circuit. So let's start with the most simple one, which is QC, for describing quantum circuit with quantum control flows. So to describe a program, I will talk about its syntax and semantics. So the syntax tells you how to write a program in this QC. So here, quantum circuits C in QC are defined by the following syntax. So this is a standard BNF form, but you don't need to know what does it mean. I will explain that. So C has the following forms. So the first cases is when C is an elementary unitary gate U applied on quantum register Q bar. So Q bar is just a list of qubits from for example, from Q1 to QM. So this is just an elementary unitary gate. And the second case is the quantum circuit C can be a sequential composition of circuit C1 and C2. So C1 can be some quantum circuit defined by the syntax, and C2 can be another quantum circuit defined by the syntax. And then their sequential composition, that is, you first apply C1 followed by C2, is also a quantum circuit. Okay, these two cases are quite intuitive. And the third cases is a quantum if statement, which is the quantum version of the classical if then else statement. So here, the QIF, we will just call it QIF statement. So QIF statement is controlled by an external quantum coin Q. So when Q is in state kit 0, it will execute the circuit C0. When Q is in state kit 1, it will execute circuit C1. So here, it's just like the classical if then else statement, but the difference is the quantum coin is quantum. So the Q can be in superposition. And in this case, the execution of C0 and C1 will also be in superposition. Okay, let's take another way to look at this QF statement. So suppose each CI, they describe a unitary UI, then the QF statement just describes a unitary of this form. So it is just a condition on the state of quantum coin Q. So if it's kit 0, then you apply the unitary U0. If it is kit 1, then you apply the unitary U1. So it's just a control version that combines U0 and U1. And the control qubit is the quantum coin Q. Okay, and this unitary is also known as a quantum multiplexer. And in this language QC, we will not consider the measurements for simplicity. And actually, all the language we will describe today will only focus on the unitary and quantum circuits composed of unitary gates. Is there any question about the syntax?
Sorry, I want to clarify the multi lecture only refers to the unitary part, and the whole part is C, containing both unitary and sequential circuit. Is that the case?
So sorry. What do you mean by C contains in the unitary?
I mean, what's the vertical line in front of there is C1 and C2, right?
Right.
So
yeah.
it means this C0, C1 is different to the C1 and C2 before, right?
Oh, okay. Yeah, so here each C1, C2, and C0 and C1, they have the same form of C, so they are just the renaming of C. So,
so it means that it's other subroutine. Can I consider it this way?
Yeah, you can consider here C0, C0 and C1, they are also defined by this syntax. So, for example, C0 can be this U, and C0 can also be a sequential composition of C1 and C2, where each C1 and C2 are unitary, or other forms.
Oh, the vertical means or, right?
Yeah, the vertical means or. Yeah, it just describes the form or structure of this C.
Okay, I see. And what's the difference of first one and the third one? I mean, the third one is a superposition of different control of unitary, and the first one is also controlled by a quantum coin. So
the first one is just a unitary applied on quantum register Q bar. So it does not specify any control.
But the coin can also be like in superposition, right?
Yeah, of course. Actually, for the first one, we do not refer to Q as a coin. It can be 1 qubit or 2 qubit or 3 qubit, and U might be single qubit gate like H, X, Y, Z, and or C naught. Any elementary unitary gate can be in the first cases.
Okay, I see. Okay, good. Okay, thank you.
Okay, thank you for this question. Okay, let me continue. So we have already explained the syntax for the language QC. Now I will talk about the semantics. The semantics will tell you what a program in QC means or how to interpret such a program. So we will focus on the operational semantics of quantum circuits in QC, and it is defined in terms of transitions between configurations. So the transition is like you are given a machine, and this machine reads this program, and the machine execute one step by step according to this program. So the transition is denoted by the right arrow, and each configurations will consist of C, which is the circuit remaining to execute, and kit per psi, which represents the current quantum state. So what does it mean for this step, for this transition? So here C is a circuit, and if you execute C or execute some part of C, it will become the quantum circuit C prime, and the current quantum state will become kit per psi prime from kit per psi. So this is transitions between configurations. Now, to define these transitions, we will have a series of transition rules. And let's start with simple ones. So this is a gate rule. So if here C is just a unitary gate applied on quantum register Q bar, then after one step of transition, the program will terminate, which is represented by this down arrow. So after execution of the unitary gate, the program terminates, and the quantum state will become this quantum state. So you just apply this unitary on the quantum register Q bar and does nothing on other qubits. and you just apply it on the current quantum state kit per psi. Okay, this is unitary gate rule, which is quite intuitive. And we also have the rules SC for the sequential composition. So here the symbol, the vertical line means given the transition above the line, we can obtain transition below this line. So suppose we are given some transitions of the C1 to C1 prime, then we can obtain transitions for the sequential composition of C1 and C2. So what is the transition? We just replace C1 by C1 prime, which intuitively means you first execute C1, then execute C2. So here, this transition means you first execute C1, and it becomes C1 prime, and the state also changed from a kit per psi to kit per psi prime. Okay, so this is the rule for sequential composition. These two rules are quite intuitive. Now let us focus on the QIF rule for the quantum if statement. So this rule is actually an equivalent expression of our previous quantum multiplexer interpretation. So it just said the quantum if statement implement the quantum multiplexer. Okay, so what is this rule? We can assume that the current quantum state is expressed as a linear combination of two states according to the computational basis of the quantum coin Q. So the first state has kit 0 in the quantum coin Q, and the second state has kit 1 in the quantum coin Q. And this is just a quantum superposition or linear combination. And we also assume we are given transitions of each CI in two quantum branches. So here, each CI determinates after some steps of transitions. So here, the right arrow star represents you take several steps of transitions, and now CI terminates and takes quantum state kit theta I to kit theta I prime. Given this, using this rule, we can obtain transitions for the quantum if statement. That means after one step of transition, the QIF terminates, and the quantum state will becomes this quantum state. So the difference is you changed each of the theta 0 to theta 0 prime and theta 1 to theta 1 prime without changing this quantum coin. And this is done in superposition. So the first execution of C0 changes theta 0 to theta 0 prime, and the execution of C1 changes theta I to theta I prime, theta 1 prime, and they are done in superposition. Okay, so this is just formally explaining our previous syntax. Now we can move on to the second language, which introduces classical variables. So second language is called QC+. Why do we need classical variables? This is because the recursion would require classical parameters. For example, you can call a procedure P with some classical parameters N. So to describe such parameters, we need classical variables. So again, we will write the syntax for this QC+. And compared to QC, we need to add these standard classical statements. So again, this vertical line stands for the OR, and we can add some classical statement. So the skip stands for you just do nothing. And this is a classical assignment. So X bar is a list of classical variables, and T bar is a list of classical expressions. So you just assign the values of T bar to X bar. This is a classical if then else statement. Here B is a Boolean expression. If B is true, then you execute C1. If B is false, then you execute C2. This is a block statement which declares the variables x bar as local variables. So what are the difference between local variables and ordinary variables? So local variables, they are initialized within this block to this value of t bar, and they will restore their old values at the end of this block. And we will see their semantics later. So these are rather standard classical statements. Is there any question at this point?
Can you explain again what's the bar here? X bar and T bar.
Okay, bar here stands for a list. So so bar X stands for X1 to X2 to XM, where M is not determinate, not deterministic. So it can be a list of 2 variables, or a list of 3 variables, or a list of 4 variables. And this assignment will assign the whole list simultaneously.
Oh, I see. Okay, good.
Okay. Okay, let me continue. So we can also define the semantics for the QC plus. But now we have classical variables. So we need to change our configuration to take into account the classical variables. And we add the sigma, which represents the current classical state. So here C is again the remaining circuit to execute. Sigma is the current classical state, and kit psi is the current quantum state. We can also talk about transition rules. Now we only select the QF rule for illustration. So here, what is the difference between these QF rules and our previous QF rules? So we have this additional sigma here, and it becomes sigma prime. And here, we need to note that these 2 different branches, C0 and C1, takes sigma to the same sigma prime. And this is a requirement which forces the classical variables to be disentangled from the quantum variables. So because these 2 quantum branches take the same classical state to the same classical state, the classical variable will remain classical after these transitions. So here you can write C prime here, separated from the quantum state. Otherwise, if you assume this sigma has a subscription I, that means if you have sigma I here and sigma I prime here, then sigma I will depend on the state of the quantum coin and become entangled with the quantum coin, which is undesirable because we want to separate the classical part and the quantum part. Okay, this is a requirement, and which looks quite strong. So how does a programmer satisfy this condition when the programmer writes a program? So we can use the local variables. Now this is rules for the block statement, which explain the local variables. So for a block of this form, we can have these transitions. So the first step is just the assignment. That's quite usual, and you execute C. This is also usual. But at the end of this block, we need to restore the old values of X. So here is another assignment which restores these variables X bar to their old value, sigma X bar. So the key here is the values of X bar before and after this block will remain the same. That is the sigma of X bar. So intuitively, that means the block statement does not change these local variables. So if we use block statement within these 2 quantum branches, they will not change the classical state. So we'll meet this condition. Okay. Now we have classical variables. And the last step is to add procedural calls. and we can obtain the language RQC++, which supports quantum recursive programs. So the procedure core has a form P of bar T. So when you write P of bar T, you call the procedure P. P is the name of this procedure, also known as the procedure identifier, and you insert these actual parameters T bar. And you have a procedure call for PT bar. So how do you define the procedure P? So we also need a set of procedure declarations. So this is like when you write a C program, you define a lot of functions. So these procedures are just the functions. And this is a declaration of the procedure P. So it defines P by the quantum circuit C. So C is called the procedure body of the procedure P. And here U bar is formal parameters of U. And we will see these later when we go through the examples. And the transitions again has configuration involving both the classical and the quantum state. And we only have this additional rule for recursion. So which explain what does a procedure call means. So for a procedure call P of bar T, we only need to replace it with the procedure body C, which defines P. And of course, we need to substitute these formal parameters U bar with the actual parameters T bar, and they are local variables. So it's just replacing every procedure call by the procedure body. So when does the recursion happens? The recursion happens when the procedure body contains P itself. So actually you are defining P using P itself. So that's where recursion happens. And when does a quantum recursion happens? So recall we have this QF statement, which can create quantum branches. So these two quantum branches are in superposition, and each of the branch can call P itself with probably different classical parameters. So this will allows you to write quantum recursions. Okay, so let's end this part with an example to better illustrate the previous concepts. So here is a very simple example of multi-controlled gate. So multi-control gate is a generalization of the single control gate. So for single control gate, we all know the C0 or CZ. These are single control gate with a single control qubit. Now multi-control gate has many control qubits. So here we write a multi-control gate by C star U, and it has n-1 control qubits, and the last qubit is being controlled. So if all of these control qubits are 1, we will apply a unitary U on the last qubit. Otherwise, we will just do nothing. So this is the definition of the multi-control gate. Now, we can write this multi-control gate as a quantum recursive program in RQC++. So this is just by defining this procedure C star U with parameters M and N, and we can call this procedure C star U on actual parameters 1 and N, and it will perform this multi-control gate. Now I will explain this program. So this is a procedure body that defines this procedure. So if M is equal to N, that means there are no control qubits. So you can just apply a unitary U on the nth qubit, denoted by Qn. Otherwise, we need to check whether these control qubits are 1 or 0. And this check needs to be done in quantum superposition because the control qubit can be in superposition. So here we use a QIF statement. So if Qm the mth qubit is kit 0, then it belongs to the second case. We just do nothing and you use the skip to skip. That means you do nothing. If QM, the mth qubit, is kit 1, then we need to move the checker one step forward. That is, we check the next qubit, and we call the procedure C star U itself with M replaced by M plus 1. So here is the recursive procedure call. The procedure C star U is defined by itself, but with different parameters. Okay, so this is a program for describing the multi-control gate. Is there any question so far or comment?
Okay.
Sorry.
Yeah, sure. You can go ahead first.
Okay. So I just have some small questions.
Yeah.
So in the else QIF, in
Yeah.
the skip part, why you use this notation QM? There is no equal sign there. I mean, you say if it is equal to 0, then you skip. Then why you don't write the equal sign there? Or is the notation?
You're asking the notation.
Yes.
Because in our previous syntax, we have defined the syntax of QIF is just you don't have an equal sign, so it is just a grammar stuff. You just write the QIF statement in this way. So it's just how you write this QIF statement. So, but what it does is, according to the semantics, you are actually checking QM whether it is 0 or 1 in superposition.
Okay, I see. So my next question is, so you need M and N is used for recursion and also to check if the recursion stop, right? If you continue change M, and if it's equal, it means that you check all the qubits and then okay, I see. And the C star just means multi-control here.
Yeah. It means you don't know how many qubits for control. Yeah.
Okay, good. I think I'm good. Thank you.
Thank you. Is there any other question?
Yeah, well, I mean, it's sort of like maybe the question is really not this one, but so here, because you have this control where you're looking for all of the qubits to be 1 or otherwise, but but this will generalize if now I really care that the controls will be some kind of bit string. So let's say for different bits combination, I want to do something different. One can still sort of generalize this, right?
Yeah, of course. You can write it, of course, in the quantum recursive program, but in a more complicated way.
Okay. I guess like when you do the QIF, then you're just checking whatever. Okay. Okay, I can imagine. Okay, like it will look a bit more complicated. Okay.
Yeah.
Okay, sure. Yeah, we can move on.
Okay, thank you. Okay. So I will continue.
Probably I have a quick question.
Oh, sure.
Actually, previously I have a question that why when you apply the circuit to the state, and see why you keep booking the circuit. I mean, usually you get a state, the new one, and
because so you are asking the transitions, right?
Yes. Why you keep booking the C prime? That's because you're trying to use the recursion, right? Or there's any other reason?
Keeping this C prime is not for the recursion, but it is just a way to define the operational semantics. Because this one step does not mean you have already executed all gates in C. So it might be you just execute a part of C, for example, one gate or a part of it, several gates of it. So you need to record the remaining. So you have a lot of remaining gates to be executed, and they are recorded by the C prime.
So then what's your like unit step? If you are now applying the whole circuit, if it could be part of it, then what's the basis unit you can apply?
Yeah. The quantum state is just you applying the part of the circuit, and for example, I will take this example. So given you have execute some part of C1 and it becomes C1 prime, then for the sequential composition, you just you also execute part of C1 and it becomes C1 prime, and the state is keep tracking the current quantum state. So our goal is to achieve this termination. So that when we obtain this termination, then the state is the final output state. Does this explain your question?
Yeah, I think kind of, but I just want to check. You see, you said the transition will make the C become C prime and psi becomes psi prime, but it could be part of the circuit applied, and the psi prime is C already been applied and psi and get psi prime, and C will become.
Oh no, the psi prime is not C already applied, but just when. So it's like given a quantum circuit and you are checking in the middle of the quantum circuit. So you just apply part of C and the remaining part is C prime. And at this point, the current quantum state is psi prime.
So you draw a circuit and you just check a different time step.
Yeah, you can understand it in this way.
Okay, I see. Okay, good. Thank you.
Oh, okay. Thank you for this question. Okay, now I will move on to the proof system. So we have already described a language for describing quantum recursive program, and we have shown by examples that you can describe some unitary gate or quantum circuit in this language. Now I will answer the question at the beginning of this talk, that is how to verify the correctness of a program in such language. So first, we need to specify the correctness of a program in this language. So the specification is the standard way. Like many other languages, we will use the precondition and post-condition to specify the correctness. So this is often known as a Hoare triple. A Hoare triple consists of 3 parts. The first part is a precondition. Then C is the program, and the third part is the post-condition. And this Hoare triple intuitively means starting from some states that satisfy this precondition, after executing C, the state after execution will satisfy the post-condition. So here, every condition consists of classical part and quantum part. The classical part is just a classical first-order logical formulas. For example, A can be these formulas where X and Y are classical variables. And the quantum part is just the current quantum state, just like our transition rules. And these quantum states can be defined by classical variables. For example, kit phi can be I1 to IM, where the number of qubits depends on some classical variables M. So this is a Hoare triple, and given the Hoare triple, we can talk about whether a Hoare triple is true or false. So that is the correctness of a Hoare triple. So given such Hoare triple, we say it is true, denoted by we use these symbol models to represent this Hoare triple is true if for all classical state that satisfy the precondition A, the execution of C terminates and takes the state sigma and kit phi to sigma prime and psi prime, then we have sigma prime satisfy the post condition B, and kit psi prime is equal to kit psi in sigma prime. So roughly speaking, this is just, I have already explained, you just start from any state which contain classical and quantum part, and the classical satisfy A, quantum part is just a kit phi. After the execution, the classical part satisfy B, and the quantum part is kit psi. Okay, and there is also a more general correctness known as, actually not more general, but another definition of correctness called total correctness, which takes into account of termination, but we don't have time to explain that. And here is an example of the Hoare triple. So here, we are considering when all control qubits, so we are considering the example of the controlled gates, and we assume all control qubits are 1, then the correctness of this program can be expressed by this Hoare triple. So here the classical condition is just m is less than or equal to n, which represents the number of control qubits are non-negative. And this program just takes this quantum state to this quantum state by applying the unitary on the last qubit, because we assume all control qubits are 1. So this is quite simple example. Now, we have already talked about the Hoare triple and its correctness, but we need to know how to prove the correctness of Hoare triple. So given a program, and we can specify its correctness, which indicates what we want this program to perform. But we also want to prove that this program really correctly performs our target. So we will have a series of proof rules to prove the correctness of a Hoare triple. So these are like transition rules, but they are more on the grammar level. So for example, for the gate proof rule, if the program is a unitary gate, then it will not change the classical condition, because the classical condition describes the classical variable, and you are applying a unitary, so it does not change the classical part, and it will only apply the U on the current quantum state phi. So that means this Hoare triple is provable. And the sequential rule is also quite similar, and we will not explain that. For the QF rule, so we will assume both quantum branches has the same classical pre and post condition A and B, and we can combine these two Hoare triple to obtain a new Hoare triple like this. So they also have a classical pre and post condition A and B, and the quantum state, the change of the quantum state is just like the transition rules of the quantum if statement. So due to the time limit, I will not get into the detail of this rule, and we will see them in the example part. So let's get quicker at this point. We also have two rules for block statement and the procedure calls. So for the block statement, these rules allows you to declare some classical variables as local variables, as long as the variables are not used in the post condition. And the instantiation rule just allows you to replace the procedure call. You can replace the parameters in the procedure call by some expression T bar, and this substitution also needs to be done on the pre and the post conditions. Okay, I will give a more careful explanation of the final rule, which is the rule for proving the recursion. So we will introduce a new symbol V dash to denote provability. So the provability means, for example, here we have this Hoare triple and V dash another Hoare triple. It means you can obtain this whole triple from this one using the previous proof rules. So this is a provability symbol. And what is this recursion rule? Actually, it is essentially a form of mathematical induction. You first assume the correctness of PT bar itself. And if you can prove using the previous proof rules to obtain the correctness of the procedure body C that defines this procedure P, of course, you need to substitute the formal parameters with actual parameters. That in this way, we can prove the correctness of PT bar. So the message here is this rule is essentially a form of mathematical induction. And later, through examples, we might get a better understanding of this rule. For simplicity, of course, this the above rule is only a special case, and there are more general rules. Okay. We have already described the proof system, and we have in this work we have also shown that this proof system is sound and complete. So the soundness theorem means every provable whole triple is correct. That means if you can prove a whole triple in this proof system, then it is also true. The completeness theorem is actually a relative completeness theorem. It basically says every correct whole triple is provable. So as long as actually you need to assume all true classical assertions are provable. That's the meaning of the relative. So as long as a whole triple is correct and you assume the all true classical assertions are provable, then you can prove this whole triple. Okay, so this is the soundness and completeness of our proof system, and we don't have time to explain them in details here. But we can explain through examples of how to use the proof rules in this proof system. So since there are not much time, I will start the last part of this talk, which is an example of proving the correctness of control gates. So here is the program of our previous example of control gates. And let's try to prove the correctness of this program using the proof rule I have already mentioned. So our goal, I will only focus on the case when all the control qubits are 1. So our goal is to prove in this case that the C star UMN will satisfy this whole triple. And here the classical condition is again m is less than or equal to n, meaning the number of control qubits are non-negative. And we will use this notation kit psi and kit psi prime to represent these two quantum states. Where kit psi prime is just applying the u on the last qubit. Okay, so how to prove that using our previous proof rule? The idea is using the rule recursion and the rule block. So remember, the recursion rule is just the mathematical induction. So we need to first assume the correctness of C star UMN. And our goal is to prove the correctness of the procedure body on the right-hand side. And assuming these the correctness of these C star UMN, we can use the instantiation rule to obtain the correctness of the with different parameters. Then we can prove the correctness of the procedure body. So let us go through this example step by step to see how to prove that. So the first step is just assuming the correctness of the procedure itself. So we assume this whole triple. The second step is by the instantiation rule. So instantiation allows you to replace the parameter m by m plus 1. So we just replace every m by m plus 1 in this Hall triple. And you obtain this Hall triple. Now, the next step is to use the QIF rule. So as you can see, in this Hall triple, the number of qubits is actually n minus m. And we want to add a new qubits to this quantum to this Hall triple. So by the QIF rule, we can add the additional quantum coin. Here, the quantum coin is in state kit 1. So it is actually a special case of the previous QIF rule. You have the amplitude alpha 1 to be 1 and the amplitude alpha 0 to be 0. So in this way, we can add a quantum coin into our system. And this quantum state actually corresponds to the quantum state of the mth qubit, QM. Yeah, and actually here kit 1, kit psi m plus 1n is exactly kit psi mn. So here we are using the recursive definition of the quantum state kit psi. And similarly, we have kit psi prime here. Okay, so this is finished the first part. So the first part deal with a case when m is less than n. So there is another part for the boundary case when m is equal to n. So in this case, that means we have no control qubits. So you just apply the unitary u on the last qubit qn. And to obtain this Hall triple, we will use the gate rule, which deals with the single elementary unitary gate. Now we have the two cases for m is less than n and m is equal to n. Now we need to combine these two Hall triple. To combine these two cases, now we will use the if rule, which is not presented previously, but it's just to combine these two different classical conditions. So to combine them, we will obtain the condition m is less than or equal to n. And the quantum state are just kit psi here. And the post condition will also have quantum state kit psi prime. So we can also combine these two statements by this if statement. So remember the if, the statement within if is already the procedure body on the right-hand side. So we have obtained the correctness of the procedure body by assuming the correctness of the procedure call itself. So finally, we can use the block rule and recursion rule to obtain the correctness of our whole procedure. And as long as we can prove it by the soundness theorem of our proof system, it is also true. So that means this program correctly performs the control gate when all the control qubits are 1. And the other case can be also proved similarly. So this is a whole proof for the correctness of the control gates. Is there any question at this point?
I guess there's none at the moment.
Okay. Sorry, I go through this quite quickly because we have already answered some questions previously. But the intuition is just we developed the proof system and we can apply these proof rules step by step and to obtain this correctness of this whole program. Yeah, and all of this is based on this program has a structure, and our proof rules are also following the structure of the program. And okay, we will skip this comment. Okay, the second example is quantum Fourier transform, but we don't have time to get into the detail. Here, I only want to mention that the idea is similar, but we need some auxiliary rules to prove the correctness. And these auxiliary rules are needed to promise the completeness or relative completeness of this proof system. More examples can be found in our paper. We actually have written the proof for the correctness of the following example, including the generation of the GHZ state and quantum state preparation, and also a circuit implementation of quantum random access memories, which is known as a QRAM. Okay. Now let me wrap up. So in this work, we have developed a programming language RQC++ for describing recursively defined quantum circuit. And we also have developed a corresponding proof system for specify and verify correctness of programs in this language. There are several future topics to be explored. So the first topic or question is whether we can find more examples or algorithms with quantum recursion and can be written in the programs in RQC++. The second topic is to implement such proof system in software, so we can use the software to automatically prove the correctness of programs. And the third topic is to find applications to recursive data structures, recursive quantum data structure. So this has been recently studied, and we expect that this recursive quantum data structure might be important, and we want to know the connection between this data structure and the recursive quantum program. So that's the end of my talk. Thank you very much. Please feel free to raise any questions and comments.
Okay, so yeah, thank you for the very interesting talk. A bit sort of like fast towards the end, but I guess like that's just a time constraint that we have. Yeah, so maybe I'll open the floor for maybe one or two quick questions. I don't know. Okay.
So thank you for the nice talk. I just want to ask, your proof is in which level? That means because you have the recursive RQC++ language, then you have the soundness and correctness.
Yeah.
But you are proving the language correct. I mean, the correctness and soundness is a theorem or is an assumption that you can use to prove the different examples, because the example you show are you are saying that you can prove this is soundness and correctness, but it's for this example, particular example, but you're defining a language. So in which level you are saying about your proof? Do you understand my question?
Okay. So let's first come back to the soundness and completeness. So actually, we have developed a proof system, and we have first defined the proof rules for this language RQC++, and we actually have proved two theorems. So these two theorems promise that this proof system is useful in the sense that it is sound and complete. So we have shown an example of proving the correctness of multi-control gate. That's a proof. We write the proof. But how do we know this proof is, you prove that, but you don't know this is a correct proof. So the soundness theorem says, as long as you can prove anything in our proof system, it will be correct, or it will be true. And completeness, relative completeness says, as long as your specification is a true specification, that means you specify these control gates correctly performs these operation, then we can prove it in our proof system. So these are explanation of these two theorems of our proof system. And when you're asking the level of the proof, so it's mostly at a high level, which is the same level as a language. So the language has these structures, and we are proving as this programming level.
Okay, so basically you are developing a proof system, and you also show it works.
Yeah.
So when you are using this for verification, I mean, in the real case, you are given a circuit, quantum circuit, and you want to verify it is correct or not, or does it achieve your goal? And so you need to rewrite this circuit as a language following your rule, and then you check the proof. Is that the case?
Yeah, that's right. But typically, we are considering this high-level programming or a quantum recursive program because we believe this quantum recursion allows you to write very complicated quantum circuit by very simple quantum program, and we only need to verify the correctness of this program. So actually, our target is not translating a quantum circuit into a program and then verify it. We just want the programmer or the algorithm designer to directly write quantum recursive program to describe their algorithm, so they can skip the step of the quantum circuit. Then you can verify the correctness of this algorithm in the formal programs.
So once you prove the correctness of this program, and in real use, you need to rewrite as a circuit, right? You need. Okay.
Yeah, that's a good question. So then another topic in the future work would be compiling this program into circuit. So the program is a high level. So you can take some compilation, just like you are compiling a classical program into instruction, low level instructions for the hardware to implement. So here quantum circuit are at a lower level. So our program is at a higher level. Once you have verified its correctness, you can develop a process of compiling this high-level program into a low-level quantum circuit. So that's the next step. Yeah.
Okay, good. Thank you very much. A very nice talk. Thank you.
Thank you for these questions.
Okay, I think like at least for the official talk, I'll end it here. So I will be ending the recording, but people who still want to ask questions can still ask afterwards. Yeah. So again, thank you for the wonderful talk. So that's it.
Thank you all for being here today.
Yeah.